Okay, I think we can get started. Welcome to the M Cubed Weekly Seminar. Today we have Joseph Chan. Now, I usually write these things, but this was so well done, I could hardly improve on it. So I'm going to read it as it appears. Joseph Chan hails from the tiny, sunny equatorial island nation of Singapore, where he obtained his bachelor's in physics and from the National University of Singapore. He obtained a PhD in meteorology and atmospheric science at Penn State University in December 2022, and he's currently an ASP, postdoctoral fellow. In January 2024, Joseph will be joining the Department of Geology at Ohio State University, his alma mater's football nemesis, as tenure-track assistant professor. Now, the goal of Joseph's career is to improve Earth system forecasts and research accelerating data sets through big data geospatial fusion of observations with numerical Earth system models. More specifically, Joseph is a data assimilation specialist. His research is centered around improving the usage of under or unutilized observations in data assimilation and developing the computationally efficient data assimilation methods to enhance forecasts and data sets. Outside of research, Joseph is an avid gardener of pollinator plants and flowers, lives in perpetual adoration and servitude of his orange feline overlord Pumpkin, whom you'll see in a minute. And the title of the talk today is Improving the Analysis and Forecast of Tropical Mesoscale Convective Systems by Advancing the Ensemble Data Assimilation of a Satellite Infrared Imagery. Joseph.
Thank you, Rich, for that wonderful introduction. And here is Set Cat. Yeah. He's quite a goofball, and like all orange cats, there's this thing about all orange cats sharing one brain cell. This is like the one time where he did it, well, one of the many times he didn't have it. So yeah, so anyway, so thank you all for taking the time to come out, especially given all your busy schedules. And thank you, Rich, for that wonderful introduction. So today I'll be talking about stuff that I did during my PhD. And which is basically on improving tropical MCS data and forecasts through advancing the ensemble data assimilation of infrared observations. So yeah, but before I begin, I would like to start with some really important acknowledgements. So first up, I would like to acknowledge my advisors, Fuqing and XC, who are cheesily standing behind each other, unintended. So I was originally one of Fuqing's students until he unfortunately passed away back in 2019, and XC joined the department around then as a faculty member, so I finished my PhD with him 3 years later. I honestly enjoyed working with the both of them, although I have to credit Fuqing with sicking a grad student on me to teach DA, who eventually became my husband. So yeah, thank him for that. I also like to thank the ADAPT group for having, so the Penn State Advanced Data Assimilation and Predictability Techniques group, for having me, especially when I start talking incessantly about MPI and memory management. I would also like to thank the NCAR Data Assimilation Research Section for hosting me back in 2019 for a ASP grad student visiting program stint. And I clearly like them so much that I am back here working with them again. And so I would also like to acknowledge my funding sources, which are the Department of Energy, the NSF, Penn State Grad School, the ASP, as well as the ONR, for ensuring that I put on a couple of inches, and for ensuring my cat doesn't ever starve. So yeah, so that's all the acknowledgements. And so let's talk about science. So as I mentioned, I'm going to just present about how we can use infrared observations to improve tropical MCS, so tropical mesoscale convective systems, data and forecasts. But the overarching theme of my research really is to try and improve Earth system forecasts. And as many of us are aware, these forecasts are generated by passing initial conditions into some kind of computer model, and out pops the four-dimensional Earth system forecast we want. So in order to improve this, from this diagram, we can tell that there are two things we need to do. We need to improve the initial conditions that go into the model, and we also need to improve the model itself. But the thing is, these two problems ultimately boil down to the same problem. We need lots of accurate and precise Earth system information, and that brings us the question of how do we obtain such information? And so as physical scientists, or like dynamicists, whatever, the first thing we reach for is often measurements. So measurements are great in the sense that they are often fairly precise and accurate. The trouble is they don't provide us with all the information we want. So for an example, what you're looking at here on the right is a map of radiosonde launch sites, basically sites that have regular radiosonde launches in continental Asia as well as the maritime continent. And as you can see, most of these sounding sites are typically a few hundred km apart, and there's basically no coverage over the ocean. So clearly, we can't learn a lot. We can learn some stuff, but we can't learn everything we want from these observations. Even though these days we have a lot of satellite imagery data, the troublesome part about satellite data is that they typically only reveal to us either 2D information or some kind of limited three-dimensional information. And even then, the exact information that's revealed by the satellite observation depends on a huge variety of factors. And so the point is, oftentimes we have a lot of accurate measurements, but they don't provide us with all the information we want. And so as a result of that, many of us turn to models. And models are great in the sense that we can get terabytes and petabytes of information out of them. The problem is that their accuracy is quite questionable at times. And so here's a little illustration of that problem. What you're seeing here is a Sumatra squall line. So Singapore is actually somewhere here. A Sumatra squall line, it's a very common event in that area. And here's a radar observation of that type of squall. And now here is a heavily tuned WRF simulation. And even with all the tuning that was thrown at it, we couldn't replicate some of the features that you see here in this observations. And so models can provide us with lots of information, but the accuracy is often questionable. And so the obvious solution then is to try and marry the two of them in such a way that we can obtain the best of both worlds. More specifically, we can use measurements to correct the model information. And the exact mechanism that I have been using to do so is through a class of data fusion methods that is called ensemble data assimilation. And so ensemble data assimilation fuses measurements and forecasts over time. And in the next couple of slides, I'll show a bunch of illustrative cartoons about how ensemble data assimilation works. And there is only one equation, no matrices. So we're good. And so for this first cartoon, so let's pretend that the real atmosphere follows this curvy trajectory with time for some observed variable. And let us pretend that there are a bunch of imperfect observations of the atmosphere. So what we do in ensemble data assimilation is that we start with an ensemble of forecasts. So we can run, say, WRF many times with different initial conditions, or something like that. And then, to fuse the observation to the forecast ensemble, that procedure typically involves pushing the ensemble towards the observation. And we call the resulting ensemble the analysis ensemble. We then, to assimilate the next observation, we then integrate this analysis ensemble forward in time, and then we repeat that pushing procedure again. And we can do this as many times as we want until we've run out of observations, or until we need to issue a forecast. At this point, you might be wondering, how exactly is this pushing process governed? How is it done? And so in ensemble data assimilation, we employ this thing known as Bayes' rule to combine our measurement information with forecast information. And I'll be illustrating that with a little example down here. So let's pretend we want to know what the temperature is here in Boulder. And let's pretend that there is some true temperature that's indicated there. And so as people of the 21st century, the first thing we do is to look at our cell phones, right? We look at our cell phones and look at what the forecasted temperature is. And so we can mathematically describe the forecast value and its uncertainties using what we call a probability density function, which I represent here with a bell curve. And so now let's pretend that I somehow run out of this room and stick a thermometer out. That gives me a measurement of temperature here in Boulder. And of course, measurements are not perfect, so that comes with its own uncertainties. We can express the measurement or the observation and its uncertainties using another type of something that's like a probability density function that we call a likelihood. What Bayes' rule tells us is that we can combine both pieces of information by just simply multiplying their PDFs together. And that produces what we call an analysis PDF. And this analysis PDF is always more precise than the forecast and the observation. And if done correctly, the center of this analysis PDF is usually closer to the truth than the forecast is. And so at this point, all I've shown you is sort of a 1D look at the problem. Like all I care about is temperature in Boulder. What about other variables in the weather model, like say pressure in some other location, say pressure in Fort Collins? And so ensemble data assimilation is able to propagate point measurements and turn it into three-dimensional corrections. And so the exact mechanism varies with the data assimilation algorithm you use, but for simplicity, I will show you how this works with the ensemble common filter, which is one of the state-of-the-art algorithms out there right now. And so what the ensemble common filter does is that, oh, I forgot to mention, so this guy here, this is the observed quantity. This is the observation itself, and here is the forecasted temperature in Boulder, and here is the forecasted pressure in Fort Collins. Forgot to mention that. OK, so what the EnKF does is that it starts by looking at the temperature in Boulder. It compares the forecasted temperature to the observed temperature using the Bayes rule stuff that I just showed you. And that gives us an estimate of what of an optimal sort of estimate of the temperature in Boulder. And to convert this temperature measurement into corrections for pressure in Fort Collins, the ensemble common filter then does a simple least square linear regression. So it just least squares fit of the data of a straight line to the data points. And then to update the pressure, the ensemble common filter then just shifts all of our ensemble members in a fashion that's parallel to this line until it hits the optimal temperature value. And this results in our updated or hopefully corrected pressure in Fort Collins. And so at this point, I want to point out that these regressions are not just statistical magic. There are actual physical meaning behind this sort of regression. And so for an example, what I'm going to show you now is the correlations between wind fields and a sort of a measure of cloud top height in the leading edge of a tropical squall line. And so here's the correlation. So we have, this is a storm relative longitude versus pressure. And we're talking about a cloud that's right here in this column. And so what I want to draw your attention to are these dipole patterns that's in the upper atmosphere and in the lower atmosphere. What that actually reflects is a sort of a conceptual idea that when we have taller clouds, we typically have stronger circulations that are associated with that. So these relationships are physical in nature, and we are actually capturing them on the fly through our regression processes. Given that ensemble data assimilation can be used to convert point measurements into corrections for the entire model, it is heavily used in weather forecast and data production. So like your favorite data set like ERA5 or the GFS analysis is all produced by DA. As such, improving ensemble data assimilation will thus improve forecasts and data production. And so that's like a sort of a 12-minute primer on how exactly data assimilation works. And now, let's talk about the stuff that I actually do, which is to use ensemble data assimilation with geostationary satellite infrared measurements. And so I am interested in these measurements because we can get them at really high spatial temporal resolution. And so these days, these data have such high resolution that you can practically watch the evolution of tiny little convective elements from them. As such, an outstanding question in the data assimilation community has been whether we can improve weather forecasting with infrared data. And I think there has been a lot of interest in this area, and I think over the past 8 years or so, there might have been like, what, 20-some papers published on this subject. And so there are a number of findings that are common to all of these studies. One really common finding is that infrared data assimilation can improve the estimates of the cloud field. So for an example, here's a case study that was done using Hurricane Harvey. And right here, what you're seeing are the observed cloud fields versus that of an experiment that did not utilize those infrared observations, and versus one that actually did use those observations. And as you can see, the cloud fields from this third column over here is a lot more realistic compared to the experiment that didn't use infrared. And another common finding is that the assimilation of infrared observations seems to improve the forecasts of tropical cyclones and mid-latitude weather systems. So here's a figure from the same paper, of the same case study of Hurricane Harvey. Black is the best tracked data. Red is the wind forecast from an experiment that used infrared ops and one that did not. And as you can see, using infrared ops seems to improve the maximum wind speed for this case. And so that's basically what has been done in the field for a while. Now, but when I started my PhD, there were two really big knowledge gaps in this area. First of all, no one has looked into what happens when we use these observations with tropical MCSs. And so I am personally interested in MCSs because where I'm from, we get most of our rainfall from these systems. And so I have a personal reason to go look at them. But of course, for societal reasons, they're societally important simply because most of the rainfall comes from them. And honestly, prior to my work, I've only been aware of one published study that examined the possibility of using infrared observations for tropical MCS. And that study was heavily idealized. There wasn't like any real data studies done at that point. And so another big knowledge gap is, how can we better handle the way infrared measurements are related to model variables? And so as it turns out, the relationship between infrared values versus something like, say, precipitable water can vary depending on whether or not you have a cloud in your ensemble. So if you have a mixture of clear and cloudy members, you end up with your ensemble starts to look like it has this curved relationship with respect to infrared. And at this point, if your alarm bells are ringing, you're absolutely right. The problem with infrared then is that it violates this linearity mechanism that we're using in the EnKF. And so a part of my work is then to try and address this sort of violations. As such, for my talk today, I'm going to be talking about two big aspects of my work. Basically, applied data assimilation work, where I apply infrared observations onto tropical MCSs and see what happens. And then more of a pure data assimilation work, where I created a new data assimilation algorithm that can better handle those nonlinearities that I spoke of. And so now let's talk a bit about the applied work. And so first I'm going to show you a demonstration using a case study of a tropical squall line to see what we can do with infrared observations. And so here's the case study in question. So this is a fairly typical kind of squall line over the Sumatra-Borneo region. We have a squall line that basically started, where did my mouse go? OK, a squall line that started over the eastern part of the Indian Ocean, and then it propagated eastwards, made landfall in Sumatra. This is Sumatra here, around May 31st. And then it terminated off the southwestern coast of Borneo on June 2nd. And so to So in this study, an interesting thing we found was that the infrared observations were able to improve the position of the simulated squall line's gust front. And that was a little surprising for us, but I'll explain that in a moment. But here's the evidence of that. And so what you're seeing here are storm relative longitude time diagrams for an experiment that did not use infrared observations and an experiment that did use infrared observations. In both cases, soundings as well as atmospheric motion vectors and surface observations were all used as well. So the only difference here is the infrared. So the colors indicate the simulated gust front. And the black contour indicates the observed clouds. And so in a squall line, one would expect the gust front to be aligned with, to be basically co-located with the clouds. But however, as you can see, without infrared observations, our simulated gust front is displaced east of the observed cloud field. So that indicates that our squall line is probably a fair bit further east than the actual squall line was. With the assimilation of infrared observations, we were able to improve that co-location. And so now here's the reason why this was surprising to me when I first saw this. And so the infrared observation I'm using here are water vapor channel infrared observations. They don't see the surface. All they see essentially is the cloud top. And so our thinking is that the infrared observations improve the gust front position because of two things. One, remember the diagram earlier that showed you about how the cloud top height is tied to the circulation? So there's that kind of correlative statistical pattern there. So we think that that's one of the reasons why, the fact that our infrared observation can basically detect where the cloud top is, in a way. So we think that that's one of the reasons why the gust front was improved. Another reason is that when we assimilate infrared observations, we tend to improve cloud fields. And with better cloud field positioning, we can improve the rainfall, and that is important for the gust front as well. And so those are the two mechanisms that we think are responsible for this. Maybe in the future we can try and tease those two apart and see which is more important. Anyway, so another finding which we had is that we were able to improve the cloud fields of the squall line in forecasts for up to 3 hours of lead time. So this is consistent with the literature. So that leads me to my first take-home message. I've just showed you a demonstration of what infrared data assimilation can do for tropical MCS forecast and analysis. And that is, we can at the very least improve the forecasted clouds and the gust front position. And so galvanized by this research, I then went on to create a high-resolution tropical mesoscale convective system reanalysis with an acronym that is pronounced as T-Mixer. And the reason for that partly is because, well, it covers China and Sri Lanka. Now, the motivation behind this work is that we wanted to accelerate tropical MCS research by creating one of the first tropical MCS resolving data products. And the other big reason for this is to try to test the long-term robustness of infrared data assimilation. Basically, we wanted to see what kind of problems can come up if we try to use infrared data in the long term. And so here's an overview of this new data product that's created. So the T-Mixer reanalysis is available for the June, July, August months of 2017, and it's available over an area that spans basically somewhere in the middle of the Indian Ocean all the way out to the West Pacific. And this data set is available publicly at 9 km grid spacing every single hour for those 3 months. And so we just picked those 3 months because summertime convection, and we also had a couple, I think we had heavy rain, we had flooding events and severe flooding events in India back then. And so to create this new reanalysis, I assimilated more than 70,000 observations every single hour into a 9 km grid spacing worth ensemble through the Penn State EnKF. So the dominant information sources we have are water vapor channel infrared valleys from geostationary satellites, atmospheric motion vectors, aka satellite-derived winds, from, as well as soundings and surface observations when they are available. The dominant source of observations is really the infrared observations because we get them fairly frequently at high resolution. And so the big punchline for this data set is that it outperforms the ERA 5 at resolving tropical MCSs. And so here's a little snapshot that demonstrates that. So what you're seeing here on the top is the observed cloud field on just a randomly picked day in my data set, versus that from the T-mixer, versus that from the ERA 5. And as you can see, the T-mixer produces more realistic MCS features than that of the ERA 5. And not only that, and this is just a single snapshot, so I then went on to validate the cloud fields for the 3 months that the data is available, that the data was created for. And so I compared the T-mixer against the outgoing long-wave radiation data set from CISL. And as you can see, the ERA 5 generally has higher root mean square errors relative to the observations than that of the T-mixer, meaning that the T-mixer generally produces more realistic cloud fields. Aside from that, the T-mix, I have also looked into some of the MCS properties that are produced by the T-mixer, and I'd like to draw your attention to some of these curves here. So you're looking at PDFs of MCS duration as well as MCS area average rain rates. The T-mixer's PDF is denoted in blue, and ERA 5 in the solid black, and MCS statistics derived from iMerge in the dashed black line. And as you can see, consistently, the blue line is a lot closer to the dashed line than the ERA 5 is. So that means that we're definitely doing a better job than the ERA 5 at capturing these MCSs. And as it turns out, the MCSs that we captured during this 3-month periods have statistical properties that are similar to climatology. So the gray line, which is kind of tucked under the dashed black line, those are the MCS statistics from 19 years worth of data. And as you can see, the blue line is also kind of following that gray line. So that's good. So another nice thing about this reanalysis is that we captured more than 1,200 MCS cases. So and this data is publicly available. You can just go in and start digging in those more than 1,200 MCSs and do whatever science you like with that. So this data is publicly available. Here's the QR code. And if you somehow lose it or somehow, you can always email me and I'll point you in the right direction. So that's my second take-home message. And that is that we now have a high-resolution tropical MCS reanalysis that outperforms the ERA 5 at capturing MCSs. And so now on to what I think is the more exciting bit of my research, which is trying to find ways to get around those pesky nonlinear problems. And so to do that, I need to first start by understanding what kind of weird statistics we're dealing with when we have infrared measurements. And as a reminder, the reason why I started working on this is because infrared has statistical properties that violate assumptions in the ensemble common filter. And the ensemble common filter really has two big assumptions. First of all, we are assuming that the forecast errors are drawn from a normal distribution. And the second big assumption is that we assume all relationships are linear. And both assumptions are violated. And so I'm going to start by showing you some evidence of the fact that these forecast uncertainties are not normally distributed. And so to do that, I ran a bunch of 50 worth simulations over the Sumatra-Borneo region, basically the same squall line case study you saw just now. And now, when I grab so here's the ensemble mean brightness temperatures. And when I grab every single simulated brightness temperature value across space and across all ensemble members in this black box and form a PDF, we end up with this really funky looking black curve here, which is hidden under the blue and the red. So this is really not Gaussian. This is to some approximation, basically bimodal, but really there's 4 modes. But what's really interesting is that when I separate the infrared values based on whether there was a cloud at that grid point, I was able to break this funky black curve into 2 somewhat distinct PDFs. We have this red curve here that indicates the clear sky values of the infrared, and this blue curve here that indicates the cloudy sky infrared values. So they are basically somewhat distinct from each other. And just to further drive home the point, I ran more WRF simulations, this time over the Indian Ocean. And what you're seeing here on the top are the ensemble averaged infrared values. So we have this nice MCS complex over here. And when I break the infrared values based on whether there is or isn't a cloud in the ensemble member, I end up with these 2 maps that you see at the bottom. Generally speaking, for specifically in window channel brightness temperatures, the clear sky values do not go below 280 Kelvin, but for cloudy members, it tends to go below that. And in fact, this difference is so big that I had to use 2 separate color bars just to show this difference. And it turns out that this sort of dichotomy doesn't just exist for infrared values. We also see something kind of similar in terms of precipitable water. And so what you're seeing here on the bottom is the clear members precipitable water versus the cloudy members precipitable water. And as you can physically expect, when we have a cloud, that usually means that we have more precipitable water than a situation without a cloud. But this drives home my point that forecast uncertainties are not normally distributed. They have what we call non-Gaussian properties. Another big issue is that the relationships linking infrared to the model variables are not linear. And so here's an example of that. What I'm about to show you are the slopes of the regression line that links precipitable water to infrared values for clear members and for cloudy members. What I want to draw your attention to is the color bar. There's a whole order of magnitude difference in terms of the slope. So clearly, the statistical relationships are actually quite different. If I were to summarize all of the data I've showed you just now, we end up with this little cartoon here. So in essence, clear members and cloudy members have distinguishably different infrared values as well as precipitable water values. And not only that, even the statistical relationships are different. And this, as a reminder, is a problem for the EnKF because we have Gaussian and linear assumptions built into the EnKF. So I started hunting for a better method. My answer to that violation is to produce a new data assimilation method that is known as the Bi-Gaussian ensemble common filter. It really is an extension of the EnKF. What it does is to explicitly treat the differences between clear and cloudy members. And it does so by replacing the standard Gaussian normally distributed forecast error assumption with a Bi-Gaussian assumption. And with this new assumption, I add on the statement that I'm going to assume all clear members are drawn from this one bell curve, and all my cloudy members are drawn from a separate bell curve that you see here. And if you look at if you compare these assumptions to the empirical PDF that you saw earlier, you can see that the Gaussian assumption doesn't look like the empirical PDF, but the Bi-Gaussian assumption looks a lot more like it. So once we have this new assumption, I work through the math, and it turns out this assumption creates a fairly conceptually straightforward 3-step data assimilation procedure. So the Bi-Gaussian filter, in the first step, it performs the linear regression process, the EnKF, twice. So it does so for the cloudy members first, and it does that again for the clear members. And by the way, just to orientate, the black dashed line you see here is the observed value of the infrared. And the y-axis is the total humidity, and the x-axis is the infrared values. So yeah, we just performed the EnKF twice in the first step. To illustrate the next two steps, I'm going to zoom in to my diagram. And now, in the second step, what we're going to do is to delete members from the cluster that is further from the observation. And so in this situation, the clear members are further from the observation than the cloudy members, so we delete the clear members. And in the third step, we replace those deleted members by adding new members into the cluster that is closer to the measurement. So in this case, it is the cloudy cluster, the cloudy members. So I'm going to add 2 new members there to replace the members I deleted. And so from a conceptual point of view, what this does is that the Bi-Gaussian filter looks at an observation, and then it sort of gets a sense of whether the observation is clear or cloudy. And then the Bi-Gaussian filter then adjusts its confidence in whether it's clear or cloudy. So if we have a cloudy observation, the Bi-Gaussian filter is going to remove confidence in the clear members by killing them off, and then adding more cloudy members. The number of members to add and delete, it's all governed and it's all described entirely by Bayes' rule. So there is very little, there's some ad hocness in this, but there's a lot of fundamental theory work that supports this. At this point, you might be wondering, wait a minute, this algorithm looks surprisingly simple. I mean, it's 3 big steps, right? And so you might be wondering why we haven't tried this before. And as it turns out, the first incarnation of an algorithm like this happened 20 years ago. And the reason is that the earlier forms were just too expensive to use. And so here is the reason why. It has to do with the third step, where I add new members into my ensemble. And so in the earlier algorithms, we tend to evoke the traditional recipe to generate new ensemble members, which is basically to multiply a scarily large matrix to a vector of white noise. The problem is with trying to determine this scarily large matrix. So to determine that, you typically need about 10 power 12 operations just to calculate it, which means it's very expensive. And to make matters worse, the computation of L is not very well parallelizable, meaning that it's not easy to put this on a high-performance computer. And we have big parallelization bottlenecks. So what I've done is to find a mathematically equivalent problem that's a lot smaller. So in essence, instead of involving an obscenely large matrix, I am now just taking the weighted sum of the original members. And these weights can be determined up in about 1,000 operations and can be done in parallel. So in other words, this recipe works well with high-performance computing. And so here is just these 2 recipes, just for comparison. The original recipe, we had a scarily large matrix that's really difficult to deal with. In this new recipe, we just replaced that with a simple weighted sum. And the fast recipe is about 1 billion times faster and parallelizes way better than the old recipe. And so that leads me to my third big take-home message, and that is we now have a computationally efficient Bi-Gaussian ensemble Kalman filter that can handle clear and cloudy members separately. And so armed with this new algorithm, the next thing to do is to test it out and see what happens, right? And so what I'm about to show you are idealized Wirth model experiments to test this new method out. And before I go into that, I would like to briefly describe how we, as data assimilation specialists, typically test any new algorithm. The philosophy is that we start as simple as possible and then work our way up. And so for today, I'll be showing you what I like to call at times virtual reality experiments. So for those of us who do DA, this is a perfect model, observing system simulation experiments. But for the rest of us, virtual reality. And I want to point out that many novel ensemble data assimilation algorithms have a tendency to fail at this stage. They can fail in the sense that they may not perform better than the EnKF, or they might fail because it just doesn't scale well. Like it doesn't work with a high performance computing. And so I implemented the Bi-Gaussian filter into the Penn State EnKF system. And of course, with Pumpkin's help, as you can see, he's helping me debug my seg faults and keeping me calm as my blood pressure went through the roof. So yeah. OK, virtual reality tests. So in this virtual reality tests, I start by running a reference WRF simulation. And that is that's my sort of a surrogate for reality. And then I'm going to draw noisy infrared measurements from this reference simulation. And then I will assimilate these noisy measurements into an ensemble of WRF simulations and see what happens. And so the winning condition is that the Bi-Gaussian filter has to be better than the EnKF at utilizing these observations. The case study I've chosen is just something which I'm somewhat familiar with, which is tropical MCSs over the Indian Ocean in October 2011. And so on to the results. So it turns out the Bi-Gaussian filter does outperform the EnKF at assimilating infrared values, specifically window channel brightness temperatures. And so what you're seeing here are normalized humidity root mean square errors with respect to that reference simulation. So this is the one on the left is the root mean square errors for the EnKF's estimates versus that of the Bi-Gaussian filter on the right. And as you can see, the Bi-Gaussian filter generally produces bluer values. Blue is good. Blue means that we have smaller RMSEs. And I've also examined a bunch of other fields, like temperature fields, the zonal wind field, and the meridional wind field. And across the board, we see that the Bi-Gaussian filter tends to produce smaller errors than that of the EnKF. In other words, the Bi-Gaussian filter is better utilizing the infrared values than the EnKF is. And just as to sort of try a final nail on the coffin with this study, I ran a bunch of 24-hour forecasts from the EnKF's analysis versus the Bi-Gaussian filter's analysis and took a look at the humidity root mean square errors. And as you can see, in these forecast runs, in general, in the lower troposphere, the Bi-Gaussian filter has much bluer values than that of the EnKF. So this means that the Bi-Gaussian filter is producing better humidity forecasts. And these improvements persist for up to at least 18 hours in the lower troposphere. So that was very exciting. And finally, you might be wondering how expensive it is to use the Bi-Gaussian filter. And so to handle 11,000 measurements, I only added 10% extra execution wall time to the Penn State EnKF. So if you want to do a subroutine by subroutine comparison, it's actually 50%. But I think I can trim it down to something a lot smaller because I have a sense of where most of this extra wall time is happening. And so that leads me to my fourth and final take-home message. And that is that I have virtual reality tests with WRF that show that the Bi-Gaussian filter is better than the EnKF at assimilating synthetic window channel brightness temperatures. And in the future, I'll be testing the Bi-Gaussian filter with real-world infrared observations and maybe different kinds of cloud-sensitive observations. I'm also thinking about hybridizing the Bi-Gaussian filter with other nonlinear data assimilation frameworks. For an example, Jeff Anderson's new probit regression framework that's actually pretty darn cool. And finally, I'll be working on enhancing the number of times the Bi-Gaussian filter is actually called in the Penn State data assimilation system. So right now, due to sampling error issues, the Bi-Gaussian filter is only called on 10% of all infrared observations. And so that needs to be fixed. That needs some fundamental theoretical work to get around. Right now, as an ASB postdoc, I am working on trying to increase the number of ensemble members without having to run WRF more times. And so I won't be talking about that. I didn't talk about it here today, but I will show this at the International Symposium for DA in Bologna, Italy in October. I'm also working on a second version of that reanalysis product, this time at 4 km with my former advisor XC as well as his new student Sam. And we think that we can get this done by, say, the end of next year. And that's it from me. So thank you very much for your attention, and I will be very happy to take any questions.
Okay, questions, comments?
Yeah, just nice talk. So I'm a little confused about your PDF figure. If you come back your PDF figure, it sounds like you looks like you show this the PDF from the brightness temperature value themselves instead of the difference like O minus B or something. So how that seems not like error and uncertainty. That seems the so how you can do using this as non-Gaussian. Do you have the similar figure for the difference or?
No, I did not look into the difference itself. The reason is that I wanted to demonstrate that in the ensemble world, we think about the ensemble as representing the general forecast uncertainties for us. So this can have really weird shapes, and this sort of uncertainties exist even if we don't look at the observation, right? If you have no observation and this is all you have, and then that's the uncertainty you have. It's kind of a definition kind of problem. Yeah.
And when you do the virtual reality experiments, and you said you draw some random noise. Is those noise is Gaussian or no Gaussian? It depends on the different pictures or?
So for the virtual reality tests, I am drawing noise from a Gaussian distribution that represents measurement noise. So I assume that the satellite instrument noise is Gaussian in nature. But but that's distinct from forecast uncertainties.
Yes, but why then? The forecast that you also have the forecast uncertainty is Gaussian or no Gaussian?
I assume the forecast uncertainty is non-Gaussian. So basically P of x is Bi-Gaussian, and then the P of y given x is the Gaussian part.
We can discuss maybe offline.
Yeah, sounds good.
Very nice talk. While you're still on this figure, I have two questions. The first one is relatively simple. Maybe I missed it and you said it, but how do you determine a grid point is cloudy versus clear?
You didn't miss anything. I didn't say it. The reason is that, for this particular figure, I recall that I looked at the column integrated hydrometeor mass. And I think I just set a threshold of 1 gram per meter square as my threshold. So even in my implementation of this Bi-Gaussian filter, I used a similar sort of thresholding approach to distinguish between clear and cloudy members. Yeah.
Okay. Thank you. Yeah, that leads to my second question. Looking at this blue figure, I say it's non-Gaussian, but one could make an argument that it's a combination of two Gaussian distributions. And it reminds me of the trimodal distribution of tropical convection. So it sounds like you're familiar with it. So
yeah, XC tried to grill me over it during, I think he threatened to grill me with that during my comprehensive exam. But anyway, so it does have that, I think it does have that trimodal structure to it. So for an example, you see this final little peak here? That looks suspiciously like the cumulonimbus peak, right? So I think it's there in the ensemble data. So the reality is I would have wished to use more than just 2 Gaussians, maybe 3 Gaussians to account for the actually 4 Gaussians. We have trimodal convection plus a clear mode, right? So 4 peaks. But it turns out to use more, this theory and this algorithm scales up to like more Gaussians. The problem is that with more Gaussians, we need to do more clustering, and like we only have 50 members. So trying to divvy 50 members into 4 groups is kind of gives you really bad sampling errors. Yeah, it's a practical reason. Yeah. Does that answer your question? Okay.
Further questions, comments? I have a question about your first take-home message.
Let me skedaddle there.
Yeah. Yeah, so I didn't get, but when you showed the figure of with and without, did you actually have ground observations of the gust front to show that the gust front was better positioned?
Yes, we did look at, what's it called? The Integrated Surface Dataset, ISD. I forgot the full acronym. We did look at that. There was a station on an island that the squall line passed over, and we did see some improvements in with respect to that station.
Okay,
Yeah.
so the basis from this figure, though, is that you just the expectation that the green lies closer to the black outline.
Yes, it was that was our expectation, but then we later confirmed that by looking at surface data.
All right, good. Well, we will have coffee and cookies until 3:30, so please join us. Thanks again.